Hello everybody, today I want to talk about how to control two permanent magnet synchronous motor as one motor dyno set. To be more specifically, I want to control the motor on the left to be the prime mover to rotate the shaft of these two motors, and I want to control the machine on the right side to be the generator, so energy will be flowing from left side to right side and feedback to the common DC link. In order to control these two electric machines, I'm using Texas Instruments C2000 DSP microprocessor. To be more specifically, I'm using TMS320F28379D. This is a 2-core DSP, but I'm only using one core to control everything. The other core is not used at all. This is the electrical system that controls two electrical machines. The big board on the bottom side is called Launchpad. This is the brain of the whole system because it contains Texas Instruments DSP. On top of the Launchpad, you can see two small boards. These two small boards are essentially two microinverters. So the microinverter on the left side controls the electric motor, and the microinverter on the right side controls electrical generator. In order to control these two electrical machines, I'll have to know the rotor position of these two machines at every instant. This is because I'm using field orientation control, or FOC, to control the permanent magnet synchronous machine. In order to provide rotor position information to my controller, there are two ways. The first way is to use a sensorless algorithm to estimate the rotor position. The other way is to use an encoder to feed such information to my controller. In this demonstration, I'm using the second approach. Therefore, I'm feeding the rotor position information to my controller through these wires. I'm using this DC source to power up the whole system. Such DC source is connected to both microinverters. The microinverter on the left side is going to invert DC power to AC, and such AC power is going to drive the machine on the left side to spin the shaft of the whole system. The machine on the right side is going to convert part of such mechanical energy to electrical energy, and such AC electrical energy is going to be converted back to DC power by the second inverter, which is on the right side. This is the software to program the Texas Instruments C2000 DSP. It's called Code Composer Studio. This is actually the code that controls these two electrical machines. You can see it's written in C language, and it has many lines. Basically, it's a field orientation control. Before controlling the generator, I want to make sure that my prime mover works well. Let's give a command to the machine on the left side, which is the motor. It is controlled under speed mode, so let's give a speed command of 300 RPM. We can see that the machine on the left side spins the shaft of the whole system at 300 RPM. Now let's reverse the speed command. See what happens. We can see that the machine on the left side reverses the rotation speed. At this stage, I know that the motor works fine. Now let's take a look at the machine on the right side. This machine is going to be used as a generator, therefore it's going to be controlled using torque mode, which is different from the machine on the left side because the machine on the left side is going to be used as a motor. Therefore, it is controlled under speed mode. On the contrary, under torque mode, the machine on the right side is going to follow my torque command, not speed. So let's give a forward torque command to the machine on the right side to see what happens. We see the machine begin to spin forward. Now let's reverse the command for torque to be backward. We see that the machine changes its rotation direction. Under this moment, the machine on the right side is working as a motor, not a generator. Why? Because right now there is no force exerted from the machine on the left side. Therefore, the direction for the speed of the motor for the right machine has the same direction as its torque direction. So because speed and torque has the same direction, so the machine on the right side right now is actually working as a motor. In order to demonstrate the effect of torque mode control, I'm going to give a very small torque command to the machine on the right side, 0.05 Newton-meter. And the shaft begins to spin backwards, and I can easily stop the shaft using my thumb because the torque is very small. But if I increase the torque command to 0.3 Newton-meter, right now the speed has increased, and it's difficult for me to stop the shaft using my thumb because the torque has increased 6 times. Right now I'm giving a torque command of 0.1 Newton-meter to the machine on the right side. Therefore, it spins the shaft of the whole system backwards. If I give a speed command to the machine on the left side, but with a different rotation direction, this time forward, see what's going to happen. We see that the machine on the left side forcefully spins the shaft of the whole system forward, but at this time, the machine on the right side exerted a torque that is opposing this forward direction, because the torque direction is backwards. Therefore, we have transformed the machine on the right side from a motor to generator. Why? Because for generator, its torque is opposing its rotation direction. Right now, the machine on the left side is controlled under speed mode. It spins the shaft forward. At the same time, the machine on the right side is controlled under torque mode, and it is trying to stop such forward movement, but without success. It's like fighting a losing battle. Now let's disable the PWM to the machine on the left side, see what's going to happen. We see that the moment I disable the PWM to the machine on the left side, the shaft of the whole system changes its rotation direction from forward to backward, because the machine on the right side always wants to push the shaft backwards. Therefore, we have transformed the machine on the right side from a generator to a motor. For wind turbine or hydrokinetic turbine, the kinetic energy from such moving fluid is proportional to the cube of fluid speed. Therefore, if you want to extract as much mechanical energy as possible from such moving fluid, you want to control the torque of the turbine to be proportional to the square of the fluid speed. This is called maximum power point tracking, or MPPT. Now I'm going to do a demonstration regarding maximum power point tracking, or MPPT. Suppose the rated speed for the generator is 3000 RPM, and we want the generator to generate the rated torque at such speed. If follow the MPPT algorithm, this means at 300 RPM, which is 10% of the rated speed, we want to control the torque of the generator at 1% of the rated torque. Why? Because as I said before, for MPPT, torque is proportional to the square of the speed. If your speed is only 10%, as a result, the torque is only 1%. Right now, I'm running the generator at 300 RPM, and I have enabled the MPPT control algorithm for the generator. If I increase my speed from 300 RPM to 3000 RPM in a linear fashion under MPPT algorithm, this means I'm going to increase the torque of the generator in a square fashion. Let's see what's going to happen. We can see that the shaft of the whole system began to increase speed. As a result, because we are continue to increase the generator torque in a square fashion, we can hear the pitch of the generator begin to increase. Right now, we are running at 3000 RPM, and the generator is exerting 0.27 Nm, which is rated torque value at such speed. If I decrease the speed of the generator to 300 RPM, then the torque will be reduced from 0.27 to 0.0027 Nm. Right now, the generator is running under rated speed and torque condition. Let's talk about generator protection. To be more specifically, what shall we do if the generator is running above the rated speed? Well, actually there are two scenarios to be considered. The first scenario is that such overspeed is not so bad. For example, if the generator is running between 100 to 120% of its rated speed, under that scenario, we can reduce the torque of the generator to protect generator. Why? Because the mechanical energy input to the generator equals speed multiplied by torque. If you have a slightly higher speed, you can actively reduce the torque command in order to compensate for the speed increase. As a result, the mechanical input power to generator remains the same. This is exactly what's happening now. I increase the generator speed from 3000 to 3600 RPM. Because I'm actively reducing the torque, the generator can still be operated within the power range. Right now, the generator is running at 3600 RPM, and we reduce the torque of the generator so that the mechanical energy input to the generator can be kept a constant. If we continue to increase the generator speed, this will be the worst case scenario, and we really want to shut down the generator in order to protect the whole system. Let's do a demonstration, see what's going to happen if I continue to increase the speed of the generator. We can see that the generator has stopped. What happened in front of our eyes just now was really quick, but it can be explained as the following. First, the controller has detected the overspeed condition is too severe. As a result, the controller initiated a sequence of emergency shutdown procedure. The first step is to cut power to the motor. The second step is to apply maximum braking torque to the generator. In this way, the speed of the shaft of the generator can be quickly reduced. Once the controller sees that the shaft speed of the generator has dropped below a very low value, for example 50 RPM, then the controller will inject a strong DC current into the stator winding of the generator. In this way, the rotor of the generator will be firmly locked. You can see right now, it's really hard for me to move the rotor because the generator has locked the rotor position. This is the end of my demonstration regarding DSP control of two permanent magnet synchronous machines. I hope you enjoyed the demonstration. Have a good day.